Welcome to Chapter 6, Students' T-Test for Numerical Measurements, the video series hosted by me, Tim Smith, on the Workbook of Quantitative Tools and Techniques in Marketing, 2nd edition. In this chapter, we begin finally looking at more than one set of data at a time. Up till now, we've been mostly just simply plotting data, visualizing data, measuring its mean, its standard deviations, and trying to understand what that data looks like. We learned that the measurements of samples, such as the mean, may yield different results due to random sampling errors. We also learned that the measurement of samples, such as the mean, may yield different results due to real differences between the samples. At this point, we're trying to determine if, when we measure these two samples, and we're looking at the mean, this measurement of the mean, here or here, and they're different in both cases, is it simply due to random sampling error, or is it because there's some real difference between the samples? I mean, we know we're going to have different means, but because of random issues, but how do we know when it's just purely random issues or because there's a real difference? Here's an example. See, if you asked 100 people on the north side of Chicago if they like spinach on a 1 to 5 scale on Tuesday, and then do it again on Thursday, it is highly likely that the weighted average measure of do you like pizza, spinach, will vary between the two samples. Tuesday will give you one measurement, Thursday will give you another measurement. The difference is very small, but they are different. This difference is most likely due to random fluctuation about the true population mean on the north side of how much they like spinach. It is not likely to be due to a real change in the like value of spinach between a Tuesday and a Thursday. So there's an example of pure random sample error, or probably, highly likely pure random sample error. Now look at the second case. Alternatively, if you ask 100 people on the north side of Chicago and 100 people on the south side of Chicago if they like spinach on a 1 to 5 scale, it is likely that the weighted average like of spinach between the two samples, north side and south side, is different. And this difference is most likely due to a difference in spinach eating habits between the samples. Now, the question then comes, if this postulate is true, how do you tell if the difference of a measurement reveals a real difference between the samples versus a random difference just due to random sample error that has no real consequence? And that's the question we're beginning to ask now. Is it the same or is it different? Are the samples really part of the same population, or are they of two different, or are they archetypes representative of two different populations? The north side population versus the south side population. Are they really different or are they the same? To help work this out, we'll use a trick called hypothesis testing. The method of hypothesis testing begins in this manner. You assume the null hypothesis. What is the null hypothesis? It's basically saying everything's the same. Everything is the same. There is no difference whatsoever. And when you're thinking about measuring attributes of people, in many ways the null hypothesis is accurate. We all have blood. We all require oxygen to live. We all enjoy drinking water. It's necessary for our species. We all eat food. We all digest food. We pretty much all like movement and thinking and being active. We like these things. In this sense, we're all the same. We're just people. There we go. So that's basically the null hypothesis. Everybody's the same. Can't we all just get along? And any difference between measurements of different samples is due to some random sample error. And the overall mean of means is probably the best description of the population average. So the null hypothesis assumes all the samples are from the same population. We're all the same. Now, we assume this. So we begin with that assumption, which isn't a bad beginning assumption, because we have many examples where it's definitely true. Next, we try to prove it wrong. Try to prove it wrong. If we cannot determine the null hypothesis is false, if we cannot prove it wrong, we finally accept it. If we can determine the null hypothesis is likely to be false, we then reject it and we accept the alternative hypothesis, where the alternative hypothesis implies the samples are from different populations. That is, differences between measures of different samples is due to a true underlying difference between the samples. So you get it? We first assume everybody's the same, which in many ways everybody is the same. And then we try to prove, well, were we wrong? Is there likely to be, could we be wrong? And if we say we're wrong, then we say, okay, well maybe this group is different from that group. And that's the alternative hypothesis. Now, we're going to use this with statistics. And what we'll use then is a statistical test of significance. This is going to require a couple of steps. The first step is something like a p-value, or probability value, one could say it. It's a statistic describing the probability that the sample measurements differ due to random sample errors alone. Okay? So the p-value, right, it's the probability, so it's going to vary from 0 to 1. P-value range from 0 chance that the differences arose from random sampling errors, to 100% chance that the differences arose from random sampling errors alone. And we're going to use some different statistical techniques, but they're pretty much all going to give us a p-value. And we're going to be looking at this p-value to try to determine, well, is it a random sampling error or is it a real difference? Now, if the p-value is 1, we know that any change is just due to random sampling errors. If it's 0, we're pretty darn sure that it's not random sampling errors, so we reject the null hypothesis, we accept the alternative hypothesis. When the p-value is basically 0, we say, aha, they are different. But if it's not really close to 0, we say, they may be from the same population. Because we assume, as a beginning, until I'm proven wrong, everybody's the same. So that's for the statistical test. The next level of the statistical test is the significance level, or alpha. You start out with the p-value. You also require a significance level, which we'll often use alpha. You know, it looks like this. It's a Greek letter, alpha. And that's what we'll do is we'll select a significance level at which we will declare that the likelihood that the two sample measurements are from the same population is so remote, we reject the null hypothesis. So the significance level is how sure must we be before we reject the idea that they're from the same population. What's the likelihood that they're from the same population? At which you say that, you know, it's possible, but it is so unlikely, I just can't accept it anymore. It's possible, but, you know, it's just improbable. I don't believe it. I don't think we're from the same population. We're looking at two different groups. I am going to reject the null hypothesis. I'm going to accept the alternative hypothesis. And that level is going to be the significance level, denoted by alpha. So now we're going to put the p-value and the alpha together in the hypothesis test. Okay? Well, typically we'll choose a significance level of about 5%. If that p-value is greater than our chosen alpha, the p-value, remember, that's the probability the differences are due to random sampling error. So if the p-value is greater than our chosen alpha, so the probability that the two sample measurement distributions due to random sampling errors is significantly large. It's larger than our chosen significance level. So the p-value, remember, that's the measurement of the likelihood that differences are due to randomness. If that p-value is greater than our alpha, and alpha is the significance level in which we say, no, there's no chance that this is just due to randomness. If our p-value is greater than our alpha, we're going to say, the probability that the two sample measurements differ is due to random sampling errors. Now that probability is significantly large. I'm going to go ahead and accept the null hypothesis. I'm going to declare any differences between the two sample measurements due to random sampling errors. And I'll otherwise call this, the differences are statistically insignificant. It's all the same. The mean of means is the right way to measure this. Now that's if the p-value is greater than the chosen alpha. What if it's less than? If the p-value is less than the chosen alpha, we go a different route. Because that's saying that the probability that the two sample measurement distributions differ is due to random sampling errors alone is extremely small. So the chances that we found differences is due to randomness in the world is very, very remote. And so remote that I'm going to reject the null hypothesis, thereby accept the alternative hypothesis. That's when my p-value is less than my chosen alpha. My probability that they're due to randomness is less than my significance level, so therefore I cannot claim it's due to randomness. I'm going to reject my null hypothesis, accept the alternative hypothesis, declare the differences between the two sample measurements is due to real differences between the population groups. Otherwise stated, the differences are statistically significant. A lot to take in. We'll try it a couple of times in exercises, and you'll see how this works out. One of the key questions might be is why are we choosing 5% as our significance level? I mean, we can choose other numbers, but we often choose 5%, and why? We'll explain. We'll return to the subject after we've done this a few times, because by then you'll see how it works out. But for now, I'm going to try to put it in a straightforward, blunt manner. I mean, what we're saying is if the chance that the difference is insignificant is more than 5%, we say there is no real difference. If the chance that the difference is insignificant, less than 5%, or less than 1 out of 20, then this is either a really, really odd sample, or the sample is from a different population. We've chosen to declare it different. Now, we know that with an alpha of 5%, we will find differences between samples where there are none, at least 1 out of 20 times. But we also suspect that we won't 19 out of 20 times. So it'll be much more right than wrong. And in some ways, 5% is just simply a conservative choice. And we'll be more right than wrong with this choice, so we're going to go with it because it seems okay. As I said, we will return to this question in Chapter 10. So now we have the hypothesis testing. We understand we're trying to look at two samples and determine if they are the same or different. And the first example we're going to do this on is with the student's t-test. And the student's t-test works with numerical data. So that's like a 1 to 5 rating or any ratio data as well. So scores of numerical data type between two samples to determine if the differences are significant or insignificant. We're going to use the student's t-test. Student was the actual person's name who came up with the t-test. So it doesn't refer to you as a student, it refers to the person whose name was student. The t-test reveals the probability, the p-value, that the measurement distributions differ due to random sampling errors. So that's exactly what we need. We need to have a p-value, and this t-test will give you that p-value. It is extremely easy to do in Excel. There's a few aspects of t-test that we need to cover. One of them is tails, and the other one is types. Now, students' t-test says, give me one set of data, give me the other set of data you want me to compare it to, and then tell me which kind of t-test you want me to do. And the which is dependent upon the parameters of tails and types. Put simply, tails come in either one type or two type. The idea of tails is you have some distribution, and you're saying, are you looking for something just up here? If so, that's a one tail test, because I'm expecting one sample to have a higher average than the other. Okay, that's the one tail. When you have an a priori expectation, meaning before you even took a measurement, you had an expectation, then you do a one-tailed t-test. If you had no expectation, which by the way is usually the safe way to go, if you have no expectations, use a two-tail t-test. That's where you're looking for differences either way out here or way over here. Okay? Back. And erase all of that. So that's tails. That's one of the choices you have. One tail if you expect one sample to have a higher average than the other. Two tail if you didn't. The next issue is types. And there are three kinds of types that Excel will use: paired, homoscedastic, and heteroscedastic. Paired data is, well, the data has to be paired. I mean, it's like you took a measurement of a sample before you gave them an exposure to an advertisement, then you measured measures the same thing after they saw an advertisement, and you're looking for differences. Or it doesn't have to be the exact same person. Sometimes we'll have paired data where I'm looking at one group and the other group, but underneath different situations. But I've been able to pair the people due to demographic or some other psychographic set of data that says, for every person in here, I got a person over there, and I know which person matches up. You have to be told the data is paired, or you have to construct the survey, construct the research methodology to know that the data is paired. After that, we have homoscedastic and heteroscedastic. So this is more like normal data. And homoscedastic is probably the most normal data because it's assuming that the data comes from two different samples and is randomly distributed about the mean. Homoscedastic is probably the most common type of student t-test that people do. Heteroscedastic assumes that the data comes from different samples and it is not randomly distributed about the mean. The remainder of the course, you'll pretty much be dealing with homoscedastic data unless you're given a good reason to believe it is paired. At this point, we've discussed students' t-test in terms of its paired. We've also looked at the idea that it reveals our p-value. We've looked at a chosen alpha. We're going to use 5%. We revealed here how we're going to actually do the hypothesis test. We've talked about the alpha. We've talked about the p-value. I think it is time for us actually to do a hypothesis test and with a real set of data and determine if it's the same or different, these two sets of data for two different examples. So let's do that.